Let's begin. So the name of the class is Introduction to Algebra for Math Competitions, and I'm your instructor, Shreyas Shrivastava. If you have any questions, please message me in the message box or email me at shreyasshrivastava@alphademic.org. Please keep your mic muted. After each topic, I'll present some questions to test your understanding and then discuss the solutions. For those who find the questions too easy, there will be some challenge questions in the end. Most importantly, have fun. I'll try my best to make the class fun and understandable, but I'm not perfect, so if you see any mistakes, please feel free to point them out. Feel free to review the session at Alphademic's YouTube channel, and please consider subscribing as well. Okay, so here are the topics for this week. First, we're going to introduce inequalities, then we're going to go into quadratic equations, then we're going to do some factorizations, then complex numbers, and then some challenge questions. And this lesson was prepared with the help of the Introduction to Algebra book from AOPS. Okay, so for inequalities, an inequality is used to express relations between expressions that are not equal. For example, you can say 4 plus 6 is greater than 1, as 10 is greater than 1. This symbol, like the open part at the end, is for the greater than side. And we can also say 1 is less than 4 plus 6, as 1 is less than 10. Those are examples of strict inequalities, meaning one side has to be greater than the other. And then non-strict inequalities are those where one side is greater than or equal to the other side. For example, 10 is greater than or equal to 10. So that's the symbol. This means this is greater than or equal to. And then this symbol is less than or equal to. So 10 is less than or equal to 10, which is also true. Okay, so here's some operations with inequalities. If you multiply a constant a to both sides of an inequality, say x is greater than y and a is greater than 0, you have x times a is greater than y times a. But if a is less than 0, then the sign of the inequality symbol changes. So instead of x being greater than y, it's going to become xa is less than ya, because xa will have a more negative value. If we divide both sides by a and a is greater than 0, then x over a is greater than y over a. But if we divide by a for a is less than 0, we have a similar case as above, and the sign gets flipped again. So it becomes x over a is less than y over a. A general rule of thumb is multiplying and dividing by a negative number changes the sign on the inequality. As for addition and subtraction, nothing really special happens. So if you add, the sign normally won't change if you add a constant. And if x is greater than y and they're both greater than 0 and a is positive, then x to the power a is greater than y to the power a. And if x is greater than y and x and y have the same sign, 1 over y is greater than 1 over x. Okay, so here's an example question. Which number is larger? The square root of 3 times the square root of 6 times square root of 2, or the square root of 6 times the square root of 2 times root 3. So this is a simple inequality question. You square both sides, and you're gonna get for the first term, if you square both sides twice, then for the first term, this is gonna become 9 times 6 times square root of 2, and the second side will become 6 squared times 2 times square root of 3. So that's 54 root 2 times 72 root 3. And if you cancel some more terms and you square it again, you're going to get 27 for the left side and the 72 for the second side. And clearly 72 is greater than 27, so the second term is larger. Okay, solving inequalities. When you're asked to solve an inequality for x, there's no one value x that satisfies the inequality. So to denote all possibilities x that work, we use interval notation. We use this symbol, which is like a bracket, if we want all numbers greater than or equal to or less than or equal to the given value that's next to the bracket. And use the parentheses for greater than and less than. So this is a non-strict inequality thing, and this is strict inequality. You solve inequalities like you would normally solve equations. Just remember how the operations work that we discussed previously. Here's an example question. Solve 2 plus x is greater than 5 minus 3x is greater than 8. So to solve this, we first want to find all x such that 5 minus 3x is greater than 8. Then you want to find all x such that 2 plus x is greater than 5 minus 3x. We don't need to look at 2 plus x is greater than 8 because we're already accounting for this with this. The 5 minus 3x is greater than 8. So first you solve this and you're going to get negative 3x is greater than 3 since you could subtract 5 from both sides. And you divide by a, which is negative, which will be negative 3, and the sign flips. So it becomes x is less than negative 1. It wouldn't stay greater than negative 1. It just becomes x is less than negative 1. Now you look at this. 2 plus x is greater than 5 minus 3x. You can simply add 3x to both sides, subtract 2 from both sides. You're going to get 4x is greater than 3, and you divide 4 from both sides, you're going to get x is greater than 3/4. So you have x is less than negative 1 and x is greater than 3/4. But that's not possible, as if it's less than negative 1, x has to be negative, and if x is greater than 3/4, x has to be positive. So there's no solutions for this. Okay, graphing. So recall the graphing from last week. Using that, we can also graph all the solutions to an inequality. To graph the solutions for an inequality, you graph the equation as normal, and if greater than, then you use the dotted line for the graph. And if you use greater than or equal to, then you use a shaded line. The reason you do this is because if it's greater than, you don't include the graph as well, because it's a strict inequality. But if it's greater than or equal to, you can include the graph as well. And then you look at the inequality symbol. So what we do is look at all the points on either side of the line, and if the points above the line satisfy the inequality, shade that, and otherwise shade the bottom. I'll show this later. And if there are two inequalities, you just find the shaded region that's common to both graphs. Okay, so here's an example. So it's find the solution to 2x minus 3y is less than 0, and x plus 3y is greater than negative 1. So what you do is first you graph this. So 2x minus 3y is equal to 0. That's how you're going to graph it. So you're going to be like 0, 0 is a point. Then you look here, and then you're like 3, 2 is also a point. So that's my general line. So I'm going to connect this line kind of like that. Kind of something like that. So that's the graph for this one. And then you look at a point above this, and you look which point will satisfy it, above the line or below the line. So what I would do is I would just take a random point. I'll just take negative 2, 1. So if I plug negative 2, 1 into this, I'm going to get negative 4 minus 3 is less than 0, which is true since negative 7 is less than 0. So the part above the line is going to be shaded. Now you draw the second inequality. X plus 3y is greater than negative 1. You find points that satisfy this. So you're going to be like 2, negative 1. And then you can also do like negative 2, negative 4, negative 4, 1. And you could connect the line like that. And then you look, does the point satisfy when it's above the line or below the line for x plus 3y is greater than negative 1? And if you plug let's just plug in 0, 1, you're going to get 0 plus 3 is greater than negative 1, which is true. So the points above the line are going to work. So you know for this line, all the points above the line work, and for this line, all the points above the line also work. So you want to find the region that's common to both the graphs. And in this case, it's going to be this whole part right here. So it's going to be like kind of like that. Yeah. So that's your solution, this whole part right here, because it's common to both graphs. Okay, so here's some problems. I'll give you guys 2 minutes to work on them. Okay, let's discuss them. So for problem 1, it said find the solutions to the inequality 2 minus 3x is greater than 11. So what you can do is you can subtract 11 from both sides and add 3x to both sides. Then it's just going to become negative 9 is greater than 3x. Then you can divide 3 from both sides, and since 3 is positive, we can just write x is less than negative 3, and we're done. Okay, so first what we're going to do is we're going to draw the graph. So we look for the points that satisfy 8x minus y is equal to 12. So one example would be 2 comma negative 4, 2 comma 4, sorry. And then another point that would work is 1 comma negative 4. Yeah, so then we connect the line. Wait. That is not how the line's supposed to look. Okay. So then you can look at which side of the line is going to work. So if I try 0 comma 0, is 0 less than 12? Yes, it is. So this whole side to the left is the correct solution in this case. The whole left of the line, the left of the line. Okay, so this one's kind of hard because it's from Armel, but it says, suppose 4 over 2001 is less than a over a plus b, in parentheses, and that is less than 5 over 2001. Find the number of integral values of b over a. Okay, so once you notice one small thing, this problem becomes really easy. What we can do is you can simply just flip it. So how remember how we talked about, like, if a is greater than b and we do 1 over a and 1 over b, then we're going to get 1 over b is greater than 1 over a. So we can use that, and if we flip all of them, this is going to become 2001. So it's going to be like 2001 over 4, and then you're going to have 2001 over 5 here. And then over here, you're going to have b plus a. In the middle, you're going to have b plus a over a. And this is equal to 1 plus b over a. That's just 1 plus b over a. But since the sign gets flipped, it's going to be like this. So it's going to be like kind of like this. 1 plus b over a in the middle, like that. Now we can subtract 1 from both sides. And this is just going to become like 1997 over 4. And this is going to become like 1996 over 5. And then this is b over a. So b over a has to be greater than 1996 over 5, and it has to be less than 1997 over 4. So you can, like, what you can do is you can find the integer that's smaller than 1997, the closest integer that's smaller than this, and that's going to be like 1996 over 4. 1996 over 4, and that's just going to be like 499. So b over a has to be less than or equal to 499 in this case. So it's gonna be like less than or equal to 499. And then this one, you can look for the integer that's closest to 1996 over 5, but it's greater than that. In this case, it's going to be 2000 over 5, which is just 400. So it's b over a is greater than or equal to 400. Okay, so now we can use this. So b over a is less than or equal to 499 and greater than or equal to 400. So our choices are 400 all the way to 499. And since we're including both values, you're going to get 100 values that work. So our answer is 100. Okay, quadratic equations. So if you see an equation like this in the form ax squared plus bx plus c, this is known as a quadratic equation. If you're asked to solve and to find the zeros of a quadratic, typically there are two solutions, but not always. So like if you have the equation x squared minus 16 is equal to 0, and you're asked find the solutions. So you're gonna be like, what value x is it gonna be so that x squared is equal to 16? And our two cases are gonna be x is equal to 4 or x is equal to -4. Factoring is really helpful when solving these equations. For example, if you want to find the zeros for x squared plus 4x plus 5, you can simply factor that. Wait, I kind of messed this part up. One second. This should say 5, and this should say 4. So it's going to be like x squared plus 5x plus 4. Sorry, my bad. So you can factor that as x plus 4 times x plus 1. And then your zeros are going to be when x plus 4 is equal to 0 or x plus 1 is equal to 0. And our possible choices are -4 and -1. Okay, so how to factor. For a quadratic equation, if the equation is x squared plus bx plus c, and it can be factored as x plus r times x plus s, where b is equal to r plus s and c is equal to rs. So if you want to factor x squared plus 10x plus 25, you want to find r and s such that rs is equal to 25 and r plus s is equal to 10. Clearly, that's going to be when r is equal to 5 and s is equal to 5. So x plus 5 times x plus 5, or x plus 5 squared. And if you're asked to factor x squared minus 11x plus 28, we look for when r plus s is equal to -11 and rs is equal to 28. And clearly that's going to be when r is equal to -7 and s is equal to -4. So you plug that into these and it's going to become x minus 4 times x minus 7. If a is not equal to 1, you'll need some trial and error to find r and s, but similar techniques apply. Okay, so this is Vietta's formulas. In general, the sum of the roots of a quadratic equation is -b over a. That's from Vietta's formulas. You can prove that by factoring. And the product of the roots are c over a. So for example, if our polynomial is x squared plus 5x plus c, and our two roots are 3 and 4, then by Vietta's, we know that the sum of the roots is going to be the sum of roots is going to be -b by a, and a is equal to 1. So -b has to be equal to 7. So b is equal to -7. And c over a, or c, because a is equal to 1, has to be equal to 3 times 4, which is 12. So our polynomial, our quadratic, will become x squared minus 7x plus 12. All right, here's an example using quadratics. So you're asked, find a, b, just find b and c such that a plus b root c is equal to the square root of 43 minus 30 root 2. You square both sides, and you're going to get 43 minus 30 root 2 is equal to a squared plus 2ab square root c plus b squared c. As you know that a plus b squared is equal to a squared plus 2ab b plus b squared. So you can use that to get this. And then now you know a squared plus b squared times c is equal to 43. And we also have -2ab. Wait, it should say positive. positive, sorry about that. And then and the chances are c is equal to 2 because you have a square root 2 here. And then, so now you have AB is equal to negative 15. I should say positive. Okay. And A squared plus 2B squared is equal to 43. And you do trial and error again, and you get A is equal to negative 5, and B is equal to 3, or A is equal to 5, and B is equal to negative 3. Since it's positive, it's going to be 5 minus 3 root 2. I think this was supposed to say minus here. And this should have been minus. That's what I messed up with. Sorry. Okay, so here are the 3 questions. I'll give you guys 2 minutes to work on them. Okay, let's begin. So problem number 1 is t to the 4 minus 11t squared plus 18 is equal to 0. Find all t. So if we let t squared equal to something like a or something, then you're simply going to get a squared. Wait, that was bad. You're going to get a squared minus 11a plus 18 is equal to 0. Now you can use your traditional factoring techniques, and you're going to get a minus 9 into a minus 2 is equal to 0. So our choices for a are a is equal to 9 and a is equal to 2. So if a is equal to 9, then our choices for t are going to be the square root of 9, which will be 3 and negative 3. And if a is equal to 2, our choices are going to be plus or minus root 2. So those are our values of t. There's 4, 3, negative 3, positive root 2, and negative root 2. Okay, so this one says find the square root of 90 plus the square root of 90 plus the square root of 90 with like, wait, it should be like 90 and then this 90 is inside the square root. So it should be kind of like this. And then this extends like this. Kind of like that. That's how it's supposed to be. So it's like the square root of 90 plus the square root of 90 inside this 90, like that. So what you do is you let the sum equal a, let it be equal to a, and then since it's infinite, if I square it, I'm going to get a squared is equal to 90, since this square root like gets canceled out in a way, and then 90 plus this infinite series again. But since this is infinite, we can say that this is also equal to a because it goes on forever. So it's just going to be 90 plus a again. So it's a squared is equal to 90 plus a. Now it's just quadratics. You're going to get a squared minus a minus 90 is equal to 0. I can factor it, and I'm going to get a minus 10 into a plus 9 is equal to 0. Oops. And now you have two possible values for this sum. But since it's like the square root, and we talked about how the square root, it should be like negative, the positive value, like the square root of 4. If someone asks what's the square root of 4, you normally say the positive root, so 2. So our answer is going to be 10. It won't be negative 9. So our answer is 10. Okay, find all solutions to 2x squared minus 11x plus 12. This is just a easy factoring problem. You just take, you can like guess it's probably going to be like 2x and then x, because you won't really have radicals. That's kind of mean to factor that. Radicals as coefficients. So 2x and x here. And then what you do is you look for, like, you want to find a and b such that negative 2a minus bx, negative 2ax minus bx is equal to negative 11x, and ab is equal to 12. If you do that, you're going to get a is equal to 4, and b is equal to 3. So our solutions are when 2x minus 3 is equal to 0, or x minus 4 is equal to 0. So x is equal to 4 is one solution, and x is equal to 3 halves is another solution. Next week, I'll talk about another way to solve these, which is like if you don't have like nice coefficients here, it's called the quadratic formula, if you guys want to look into it a little bit early. But it's basically a way you can solve these equations without actually having to do the annoying factoring. Okay, so here's some important factorizations you should know, because they definitely pop up a lot in math competitions and even in school math. So first, there's a plus b squared is equal to a squared plus 2ab plus b squared. To prove that, all you have to do is just do a plus b times a plus b. And then you can just like, you can just distribute it using the distributed property. So it's going to be a squared plus ab, because a times a plus a times b plus b times a plus b squared, which is just going to be a squared plus 2ab minus b squared. Using similar logic, you can just be like, you can find out that a minus b squared whole squared is equal to a squared minus 2ab plus b squared. And then you're gonna another important factorization, which is really important, is a squared minus b squared is equal to a plus b times a minus b. This is really helpful to know. The reason this is true is because a times a, it's just, if you distribute it, you're going to get a squared minus ab plus ab minus b squared. And these two cancel out, so it's just going to be a squared minus b squared. And then a cubed plus b cubed, it can be factored as a plus b times a squared minus ab plus b squared. These two are also really helpful to know. You can use a similar method to prove it. You can just like distribute this. And the way you remember it is just remember, if you have a cubed plus b cubed, this plus goes into the a plus b. These are the only two signs that actually change, like the plus and the minus, and this because minus plus. So you just want to remember, if it's a cubed plus b cubed, it's a plus b times a squared minus ab plus b squared. And if it's a cubed minus b cubed, it's a minus b into a squared plus ab plus b squared. So those are the factorizations. All right, here's an example using those factorizations. Factorize x to the power 6 minus 64 as a product of 4 factors. So you can use difference of cubes, because you notice that this is just x squared to the power 3 and this is just 4 cubed. And this factors to be x squared minus 4 times x to the power 4 plus 4x squared plus 16 there. And then you can use difference of squares on x squared minus 4, and it's going to become x plus 2 into x minus 2. And for the second term, what you do is you can use the a plus b whole squared technique, and you can recognize that this can simply be written as x squared plus 4 squared, like this, and that's going to be x to the power 4 plus 8x squared plus 16. And since it's only 4x squared here, you can subtract 4x squared from that, which is just 2x squared. Okay, so far factorization is x plus 2 into x minus 2 times this thing. And now what you can do is you can use difference of squares, because you notice that this is a square and this is a square, because it's 2x squared and this is x squared plus 4 squared. So you can use difference of squares, and you're going to get x plus 2 into x minus 2 into x squared plus 4 minus 2x into x squared plus 4 plus 2x. So those are our answers. That's our answer. Those are the 4 factors. Okay. This is an HMMT problem. So this is kind of an advanced competition, but I'm just trying to show how like you could use these easy factorizations to solve these pretty hard problems. So the number 7 followed by 9 nines, it has 2 prime factors. Find them. You can write this number as 8 followed by 9 zeros minus 1. And we notice that this is 2000 cubed minus 1 cubed. You can find that pretty easily, because that's just 8 and that's 2 cubed. And there's 3 groups of zeros, so you can find that pretty easily. So then you can use this difference of cubes again. And remember, a cubed minus b cubed is a minus b into a squared plus ab plus 1. In this case, which will be 1 from that. And then, so if you factor, you're going to get 2000 minus 1 into 2000 squared plus 2000 plus 1. And remember how they told us how both the factors, you want to find 2 of them, which are prime. And since we already found 2 of the factors, we know both of these are going to be prime. We already know that. And since both, yeah, so I wrote that here. They're both prime. So you can simply do 2000 minus 1. That's going to be your first prime factor, which is 1999. And then this is just 4 followed by 6 zeros plus 2000 plus 1. So it's just going to be 4,002,001. So those are our two prime factors. Okay, rationalizing the denominator. You can rationalize the denominator if you have a radical in the denominator. For example, if you have 1 over square root of 2, you can multiply the numerator and the denominator by root 2, and you're going to get root 2 over root 2 times root 2, which is just 2. So that's now rationalized. We can use factoring techniques to solve these as well. If you're asked to rationalize 1 over the square root of 7 minus square root of 6, to rationalize this, remember the difference is squares, which tells you a squared minus b squared is equal to a minus b times a plus b. So if you multiply this, let this be a and let this be b. If you multiply a minus b by a plus b, it's going to become 1 over a squared minus b squared, which is just 1. So we multiply by square root of 7 plus square root of 6 to both the numerator and the denominator. The denominator becomes the square root of 7 squared minus the square root of 6 squared, which is just 1. And the numerator becomes root 7 plus root 6. So let's rationalize now. Okay, so this is Simon's favorite factoring trick. This is really helpful in like AMCA. I've seen this a lot, in math cons especially a lot. So I'll just show you an example to explain this. So find all mn such that mn plus n is equal to 76. So what you do is you factor this into m plus 1 into n plus 1. You notice that this, by distributive property, this is mn plus m plus n plus 1. And since there's no plus 1 here, you can simply just subtract 1. You add 1 to both sides, you're going to get m plus 1 into n plus 1 is equal to 77. And clearly m plus 1 and n plus 1 are both factors of 77. So you list out all the possibilities for each of them, and they are 77, 11, 7, and 1. And now you can just find m and n that satisfy this. So it's going to be 76, 0, 10, 6, 6, 10, and 0, 76. This trick is pretty useful and saves a lot of time once you understand properly when to apply it. So you don't just apply it if you see some random numbers like this. It's not always helpful. Sometimes it ends up like wasting a lot of time. And the main thing to understand is that if you want to factor these type expressions, you want to factor it into the form m plus something into n plus something. Okay, so here's some practice questions. I'll give you guys about 2 minutes to work on. Okay, let's discuss them. So the first one says, rationalize the denominator of 1 over the square root of 2 plus the square root of 3 plus the square root of 5. So I'll just write this out again. So the technique here, what to do is you want to you can like think of it like this. You can put parentheses on this, and you can multiply this using the difference of squares technique again, and you can do like this plus root 2 plus root 3 minus root 5. You kind of think of it like that. So then you could do a squared minus b squared. This squared is just going to be 5 plus 2 root 6, and then minus root 5 squared, which is just 5. So this just cancels out with this. And then the numerator is going to be root 2 plus root 3 minus root 5. And the denominator is just 2 root 6. Now you can multiply root 6 to both the numerator and denominator. This is going to become root 12, which is 2 root 3 plus 3 root 2 minus root 30 all over 12. So that's our answer. That's what you get, because now this is rationalized. No radical in the denominator. Find out pairs of integers b comma c such that bc minus 7b plus 3c is equal to 70. We can factor this using Simon's favorite factoring trick. So what you want to do is you look. So you want to find the constants such that you get this. You get bc minus 7b plus 3c. So first you look at this. What's going to be this constant? Since you want the coefficient in front of the c to be 3, you want this to be 3. And you want the coefficient in front of the b to be -7, so this should be -7. So it's going to become bc plus 3c minus 21 and then minus 7b. So you can add 21 to both sides in this case. Wait, 1 second. Sorry, you can like subtract 21 from both sides. And then you're going to get this is equal to 49. Okay, so now that you have that, you look for the factors of 49 that these can possibly be. So this has a possibility to be 1, 7, and 49. And this could be 49, 7, and 1. So this is 1. This is going to have b is going to be equal to -2. And if this is 49, b is equal to c is equal to 56. So that's our first pair. And then if this is equal to 7, b is equal to 4. And if this is equal to 7, b is equal to 14. That's our second pair. And if this is equal to 49, b is equal to 46. And if this is equal to 1, c is equal to 8. So that's our 3 ordered pairs. -2 comma 56, 4 comma 14, and 46 comma 8. Okay, so compute the square root of 1998 times 1996 times 1994 times 1992 plus 16. Kind of like, I'm going to put this. Yeah. All right. Without a calculator. And this is from a competition called Mandelbrot. It got discontinued like last year, I think. Okay. So if you let 1995 equal x, this is going to be equal to x plus x minus 1. This is going to be x plus 1. This is going to be x plus 3, x plus 1, x minus 1, x minus 3. We can use difference of squares, and this is going to become x squared minus 9 times x squared minus 1. You can distribute this, and you're going to get x to the power 4 minus 10x squared plus 9 plus 16. So that's just plus 25. Recall how we talked about differences squared, a minus b squared, which is a squared minus 2ab plus b squared. And this is in that form. This is just going to be x squared minus 5 squared. So if you take the square root of that, it's just going to become x squared minus 5. So our answer is going to be 1995 squared minus 5. And you can compute that pretty easily. Okay, numbers. So positive integers are 1, 2, and then 3, 4, 5, so on. They're like whole numbers, but they don't include negative numbers and they don't include 0 as well. Rational numbers are any number that can be written as a fraction. For example, root 2 is not rational, because if you assume it was rational, then it could be written as p is over q, and p would be equal to root 2q. So p squared is equal to 2q squared. So p must be even, and q must also be even. That's not possible as p over q is already in lowest terms. So root 2 is not rational, or is said to be irrational. Imaginary numbers. Now, if you want to find x such that x squared is equal to negative 4, you would assume that there would be no solutions. To fix that, Euler introduced the symbol I, which is known as the square root of negative 1. So in this case, you would try to find the square root of negative 4, which would just be 2i, plus or minus 2i. Now that I was created, we had introduced a whole new set of numbers, which would be regarded as imaginary numbers. The other group of numbers are called real numbers, which we are more familiar with. There are some important things we should know about I. One thing is that i's power repeats every 4. By this, I mean I to the power 0 is equal to 1, I to the power 1 is equal to I squared is equal to negative 1, I to the power 3 is equal to negative 1, and I to the 4 is equal to 1. So you notice that it repeats again. So I to the 0 is equal to I to the 4. So it repeats every 4. So for example, if you're asked to find I to the power 1007, that's just equal to I to the power 3, because it repeats every 4. And that's just negative I. Complex numbers. A complex number is written as a plus bi, where a is the real part and bi is the imaginary part. Any like number can technically be written as a complex number. Like if it's real, b is just equal to 0. That's the case. Arithmetic for these numbers applies the same to these numbers the same way as they do to regular expressions. So 7 plus 2i plus 4 minus 3i is equal to 11. So like 7 plus 4 plus 2i minus 3i, which is 11 minus I. Something really important to note is that a plus bi times a minus bi is actually a real number. It's a squared plus b squared. The conjugate of a complex number is a plus bi is a minus bi. Also, the conjugate can be denoted as a line above the complex number. So if you're asked find the conjugate of a plus bi and there's like a line over it, then it's just a minus bi. That's all it is. Using conjugates. So it's asking you find a such that negative 3 plus 8i times negative 3 minus ai is a real number. We talked about how complex numbers times its conjugate is a real number. So the conjugate of negative 3 plus 8i is just negative 3 minus 8i. So a should be equal to 8. Okay, and then write 3 minus I over negative 2 plus 5i as a single complex number. So we multiply the denominator by its conjugate, and then that's going to become, so the numerator is going to become 3 minus I into negative 2 minus 5i. And the denominator is just going to become a squared plus b squared, which in this case a is negative 2 and b is 5. So it's just going to become 29. You can multiply this out. You're going to get negative 11 minus 13i for the numerator, and the denominator is 29. So that's our single complex number. Okay, so here's some practice questions. I'll give you guys 2 minutes. I won't go over the challenge questions this time because we're running out of time. I'll just assign it in Google Classroom. All right, let's discuss them. First question says, simplify I minus I to the power negative 1 to the power negative 1. This is from ASME, which was like the previous version of AMC 10/12. So first we write I minus I to the negative 1, which is just 1 over I. And then you can just do the difference of fractions, which just this will become I squared minus 1 over I squared is negative 1, so this is just gonna become negative 2 over I. And this to the power negative 1 is just gonna become 1 over this, so it's just gonna be I over negative 2. So that's our answer. If A is real and A plus 6I times 5 minus 3I is a real number, find A. We can start by distributing this. So we're going to get 5A minus 3IA plus 30I minus 18I squared, which is just going to be plus 18. If we want this to be real, we want to cancel out the i's. You don't want any i's in this expression because I is imaginary. So what we do is we take a is equal to 10. Because if a is equal to 10, the i's cancel out. So our answer is 10. A is equal to 10. Express 6 minus I over 4 plus 2I as a complex number. We can multiply the denominator by its conjugate. So that's going to be the numerator. And the denominator is just going to be a squared plus b squared, which in this case will be 4 squared plus 2 squared, which is just 20. Now we can distribute the numerator, and that's going to be 24 minus 12i minus 4i plus 2i squared. So 24 minus 12i minus 4i, which is 16i, plus 2i squared, which is just negative 2. So 22 minus 16i over 20. So that's our answer. I'm going to assign these on Google Classroom because we're running out of time. Okay. Thank you for watching. Remember to check the Alphademic YouTube channel if you would like to review this session again. See you guys for the next class. Bye.